In this video, we're going to talk about a more general version of the Gauss-Jordan elimination method. In particular, how to use the method when things go wrong. Okay, so that's why we need to generalize it. So you might not always be able to get diagonal form. Okay, so there might not be one unique solution. So like I said in the last video, you could have no solutions or you could have infinitely many solutions. And we need to know how to determine which, and if there's infinitely many, how to write what they are. So there's a very nice flow chart that was actually created by another instructor at Camosun, Dr. Garrett Flowers. So you can follow this procedure no matter what your solution type. Okay, so again, you start by making your, putting your matrix in putting your system in an augmented matrix. And like we did before, you're going to consider the entry in row 1, column 1. So that's the top left entry. Just like before, you're going to say, is this entry 0? Okay, if it's not 0, then we're going to pivot around it, just like we did before. Okay, if it is 0 though, which could have happened in our previous method, you want to switch it with a row that's beneath it. Okay, so you can get a 1 in this entry. So if it wasn't 0, you're going to pivot around it, and then you're going to go down 1, next row, next column. Same idea as before, and then you go right back up. Is it 0? Okay, so this, if you get a unique solution, it means that you were able to follow sort of this path the whole time. Now, what happens if you get a 0? Okay, so first of all, you look to try to switch the row. So look for a row beneath it that's not 0 in that column. If there is one, then switch your rows and then pivot around that new entry. If there's no possible switch, what you're going to do is move over further. So same row, but go to the next column. Okay, so if that entry is good, then you're going to pivot around it. Okay, so you consider that entry, okay, is it 0? Okay, if you run out of rows and columns, then this is how you know where to stop. Okay, so then you're going to have to put the system back into its sort of equation form. So it might be nice if you have this handy for when you're first starting to do examples so that you can follow it. But you'll get the hang of it. You should get the hang of it fairly quickly. So let's try an example. Okay, this is a nice and short one. So we want to solve this system. So again, the first thing we do is put it into a matrix. So our first row is going to be 1, 2, my vertical line, and then a 3. And my second row is 2, 4, -1. So following the procedure, I should start in row 1, column 1 entry and pivot around that entry. So it's already a 1. So what I want to do is make this 2 a 0. Okay, so how am I going to do that? Well, I'm changing row 2, so I write that first. I want to subtract 2 of row 1. Okay, so again, row 1 is not changing, so I can write that in right away. And then I want to compute these entries in row 2. So I used to have a 2, and I'm subtracting 2 times the 1 above it. So I get a 0, which is what I wanted. In the next entry, I had a 4, and I'm subtracting 2 times the entry above it, which is 2. So I get 4 minus 4, which is also a 0. In the last spot, I have a -1 minus 2 times the 3 above it. So I get -1 minus 6. That's going to be -7. So I'm done pivoting in this first row. So I should go down 1, over 1, and look at this entry. This is my next possible pivot. But the flowchart asks me, is it 0? And my answer here is yes. Okay, and there's no way I can switch with a row below it because there are no rows below it. And I can't move over further because I hit this line. So I'm actually stuck at this point. Okay, so this would be in the simplified form. So what the flowchart tells me to do is write it as equations again. Okay, so here we have to remember there's an x equation, so x column, y column, the equals, and then the numbers, and each row is an equation. So I get 1 times x plus 2 times y equals to 3. And then I get 0 times x plus 0 times y equals negative 7. If I simplify each of these, so I get x plus 2y equals 3 for my first equation. But in my second equation, I get 0 times x plus 0 times y. That's just 0. So I get 0 equals negative 7. Okay, what is going on with that row? Okay, this doesn't make any sense. So what I think of when I see a row like this, I call it a bad row. Okay, and what it looks like in the matrix, okay, is like this. So what's special about it is that it has, I don't know where to write this. Okay, so it has like on this side of the line, okay, it's all zeros. Okay, and the number that's on the other side is not 0. Okay, so that's what it means to be a bad row. Because you're going to end up with something that's 0 equals a number that's not 0. So you're going to get an equation that doesn't make any sense. Okay, what does this actually mean for the system? So let's use our old techniques. And I'm going to just put both of these equations in slope-intercept form. Okay, so this is going to be 2y equals negative x plus 3. And then I divide everything by 2. I'm going to get y equals negative 1/2 x plus 3 over 2. Okay, when I do the other one, 2x plus 4y equals negative 1. I'm going to have 4y equals negative 2x minus 1. Divide everything by 4. Negative 2 over 4 is negative 1/2. And it's going to be minus 1 over 4. So notice I got the same slopes. Okay, so the slopes are equal. Okay, and the y-intercepts, okay, the y-intercepts are not equal. So what that means is that we have parallel lines, because they have the same slopes, that are not the same line. Okay, so that means that they never intersect, which means that there's no solution. So this is what's happening. Now I did it for 2 variables so that we can talk about the line and the slope of the line, but it's the same idea when you have 3 variables or more. It means that the planes or whatever, they don't intersect. So there's no place in which they're all satisfied. So that's when we have no solution. So if you get a bad row, okay, like that's what I call it, that's when we get no solution. Okay, so that's what you should see with no solution. Now, before we talk about the infinitely many case, we need some terminology because this one is a bit tougher. So we define a leading one, okay, to be the first one in a row. And a leading column is a column that has a leading one. Okay, a free column is a column that does not have a leading one. And the variable associated with that column is called a free column. So in this example, so assuming that the variables went x, y, z, w, say, we're going to have, so this one is the first one in row 1. Okay, so that's going to be a leading one. Okay, so that's going to be a leading column. Okay, so column 1 is a leading column. Okay, and this one in row 2 is the first one in that row, which means that the y column is also a leading column. Okay, in row 3, the first one appears in the column 4. Okay, so column 4 is also a leading column. So that means that column 3 does not have a leading one. So even if this number was a 1, it's still not a leading one because this one is before it. Okay, so this column has no leading 1, which means that it's a free column, which means that Z is a free variable because Z is the variable associated with that column. Okay, now we also see that there's no bad rows. Okay, so there's not all zeros and then a number that's not 0. And we're not in diagonal form. Okay, so there's not a unique solution. There's not no solution. So this is the type of thing you'll see if you get infinitely many solutions. Okay, so to find what they are, what we're going to do is write out the equations. Okay, so the system, so this is assuming it's been reduced to this. The system became x plus 2z is equal to 1. Okay, y was equal to 2 and w was equal to 3. Okay, so those are our equations. So what we normally say, because z is the free variable, that we can figure out the solutions depending on that variable. So what I'm going to do is just rearrange this first equation and solve for x. So x would have to be 1 minus 2 times whatever z is. Okay, y and w here are already determined. Okay, so it doesn't actually matter what z is. But if I know z, okay, then I know what x is because I just plug in z. So for the solutions, basically z is allowed to be anything. Okay, so when we write the solutions, okay, we're going to get infinitely many. And the way that we write them, so whenever you have solutions, you should have each of your variables equal to something. Okay, so here y is 2 and w is 3. Okay, those ones were given. Z is free. So what we write is that z can be any value. Okay, now once we pick z, x has to be 1 minus 2 times whatever z is. Okay, so these are what our solutions look like. So then if you had, say, I don't know, z equals 0, you would have the solution x equals 1, y equals 2, z equals 0, w equals 3. If you had z equals, you can pick whatever you want. It could be like root 2. Okay, then your solution would be x equals 1 minus 2 root 2, y would be 2, z would be root 2, w would be 3. You can pick whatever you want for z and you get a different solution. All of these solutions, okay, no matter what you pick for z, are going to satisfy your initial equations, which we don't have here. But they would satisfy your initial equations. They will give you solutions. So that's why you get infinitely many. Now, some other places also write, so you could see, if you look in other places, you might see something like this. Okay, so they call z a different variable. Okay, so z is like t, and then x would be 1 minus 2t, and then they would write for any real number, t. Okay, so t can be anything. That's basically saying z is any value, and then x is determined by that value. Okay, so it says the same thing, it just looks a bit different. I'm happy if you use either. Okay, so our old textbook used to use this any value thing, so I'm happy with that. But if you like to use other variables, you can do that as well. So let's just recap here. So if you perform Gauss-Jordan elimination, you get one unique solution if you reduce to diagonal form. Okay, so you could have extra rows of zeros or something, but basically you have a 1 on the diagonal for every column. Okay, so you can reduce to diagonal form. No solution if you get a bad row. Bad rows are actually good rows, because even if you get a bad row in like your first step, it tells you to stop. Okay, it means that you're done, essentially. So you get a bad row, maybe I'll just write, okay, so that looks like all zeros, and then your line, and then a number that's not 0. Okay, you get infinitely many solutions if there is a free column, at least one free column. Okay, so that means at least one free variable, okay, and no bad row. Okay, so the bad row trumps everything. So you can never have a bad row in the other two cases. If you get a bad row, it instantly means no solution. Okay, so there's at least one free column, which means i.e., so at least one column without a leading one. Okay, so let's try another example. So here's our system. Let's write it in augmented matrix. 1, 1, negative 1, negative 1, 1, 3, negative 7, 7, negative 4, negative 1, negative 5, 16. So we pivot around our first entry. So I want to make the 1 and the negative 4 below it 0. So I'm going to do row 2 minus row 1. Okay, I'm not changing row 1 here. So row 1, so I'm going to have 1 minus 1, so that's going to be a 0, that's what I wanted. And I'm going to have 3 minus 1, so that's going to give me a 2 in the second spot. Negative 7 minus negative 1 is going to give me a negative 6. And 7 minus negative 1 is going to give me a positive 8. Now I'm also going to do the negative 4 at the same time. So here I'm going to do row 3 plus 4 of row 1. So the reason I can do this, can you combine these, is because I'm using row 1 for both changes, and I haven't changed row 1 at this step. Okay, so row 1 is the same as it was before. So that's when it's sort of easiest to combine steps. So we're going to have negative 4 plus 4 of row 1, so that's a 0. Negative 1 plus 4 times 1, so that's negative 1 plus 4 is going to be 3. Negative 5 plus 4 times negative 1, so that's negative 5 minus 4, so that's going to be negative 9. 16 plus 4 times negative 1, so that's 16 minus 4 is 12. So now my method, I'm done pivoting in column 1, so I go down 1, over 1, now I want to pivot at this 2. Okay, so I'm probably going to fit this first step here, so it's going to be row 2 divided by 2, or 1/2 row 2. Okay, so everything else stays the same. So I divide everything in row 2 by 2. I'm going to get 0, 1, negative 3, and 4. 0, 3, negative 9, and 12. Okay, I'm still pivoting around that entry. So I want to make the entry above it in row 1 a 0. So I'm going to do row 1 minus row 2. Okay, now here I'm not changing row 2, so I'm just going to write it right in there, so I know it's not changing. Now I'm going to do 1 minus 0, okay, that's still 1. And then I have 1 minus 1, okay, that's a 0. And then I have negative 1 minus negative 3, so that's negative 1 plus 3, so that's going to be a 2. Then I have negative 1 minus 4, so that's going to be a negative 5. Okay, now I also want to change this 3 to a 0. So I'm going to do row 3 minus 3 of row 2. Okay, so I have 0 minus 3 times 0. Okay, that's 0 minus 0. 3 minus 3 times 1. Okay, so that's a 0. That's what I wanted. Negative 9 minus 3 times negative 3. So that's negative 9 plus 9. That's going to give me a 0. And then I have 12 minus 3 times 4. So that's 12 minus 12. That's also going to give me a 0. Okay, so I'm done pivoting in this column. So I move down 1, over 1, and now I want to pivot here, where this 0 is. Okay, it's a 0. I'm not allowed to pivot around a 0. Okay, so I should be looking below it for rows that I can switch with, but there are none. So my next step is to move over further, but I can't because I'm blocked by this vertical line. So I'm stuck. Okay, this is where I would stop. So, okay, we don't have diagonal form. Okay, we don't have a bad row because this last row is not bad because it's 0, all zeros equals 0. So that's going to be 0 equals 0. Okay, that's not a bad thing. So let's write out what this system looks like. So remember, it's x, y, and z. Okay, so that's x plus 2z equals negative 5. And then it's y minus 3z equals 4. And this last row says 0 equals 0. Okay, that's not bad. It just doesn't give us any information. Okay, so if you look at the system here, oops, okay, I shouldn't have written those there, but there's 2 leading columns, okay, that column and that column, because these are leading ones. They're the first one in row 1 and the first one in row 2. Okay, row 3 doesn't have a leading one. Okay, so there's no leading one for that row. Now this last column, is a free column. So again, that means that z is a free variable. Okay, so that means that z gets to be anything. So that's telling us that we have infinitely many solutions, because z can be any number. So when we want to give our solutions, we want them in terms of z. So what we want to do is take our equation, so x plus 2z is equal to negative 5. We want to solve this for x. So that's going to be x is negative 2z minus 5. Okay, y minus 3z is equal to 4. So we solve this for y, and I get y is equal to 3z plus 4. So that means our solutions, so we should have x equals something, y equals something, z equals something. So the z is any value, so it's allowed to be anything. Once we know what z is, x has to be negative 2z minus 5, and y has to be 3z plus 4. So if you pick, so let's just check here. So I'm going to pick a z. So let's say I pick z equals, I don't really know. Okay, I want something that's not too hard. Let's say minus 1. Okay, so that means that x has to be 2 minus 5, so negative 3. And y has to be negative 3 plus 4, so 1. So now I'm going to check those into our equations. Okay, so x plus y minus z, x plus y minus z. So that's negative 3 plus 1 minus negative 1. So that's negative 3 plus 2, that's negative 1. And that's exactly what our first equation said. Okay, the second equation is x plus 3y minus 7z. X plus 3y minus 7z, so that's going to be negative 3 plus 3 times 1 minus 7 times negative 1. So negative 3 plus 3, that's 0, plus 7 is 7. And our first equation was supposed to equal 7. So that one checks out. Third equation, negative 4x minus y minus 5z. So that's negative 4 times negative 3 minus 1 minus 5 times negative 1. So that's 12 minus 1 plus 5. So that's going to be 17 minus 1, so 16. And that's exactly what our third equation was supposed to equal. Okay, now I just selected negative 1 at random. You can pick whatever you want for z. As long as you compute x and y, depending on that z, all three equations will be satisfied. Okay, so